If your coax cable storage look like this over the years and you are not sure about the impedance of the coax cable in your store, then this video might be the right one to understand how to check out the cable impedance and a bit more about coax cable. Welcome to TRX Bench. Yeah, it is really not unusual that your storage may look like this, because over the years you collected different kinds of coax cable, and maybe you bought some at a flea market or such, and then you need your coax cable for a new project or whatever, and then you are really not sure what is the impedance of our cable, of the cable we have in the storage. And well, today let's talk a little bit about how to easily determine how to find the impedance for the cable. And secondly, I mean, we know that in most cases we need 50 ohm coax cable impedance, and then we have, of course, 75 ohm cable, more for our broadband applications like your TV or so. And well, then we have this 450 ohm cable. So I mean, this is easy to see what it is. But if you use this cable or this or maybe this, you cannot be sure if it is the right impedance, and it is not always printed on the wire. So even this here, which is so this is really a very good brand, but you do not get an information about the impedance. I mean, it is easy to look it up on Google, because it is it is called VZ. It is a German brand, and it is a MK90. So it is easy to look it up on Google. But if there is nothing written on the cable, then you are really lost, and you might not have an idea what is it, because 50 ohm and 75 ohm are not the only impedances which are available with antenna cable. So we have the older norm of 60 ohm and such. So sometimes it is different, and so the only idea is to find really what the impedance is of the cable we want to use. And the only device you need is something like this. So this is really a very cheap capacitance and inductance meter. So you can switch it between, you see it already here, farad and yeah, so this is now overrange. It is clear, because this will show you the inductance, so the L, and of course the C. So that is what the meter needs to be able to read. And these meters are very cheap in the market today's, so no problem anymore. Even this year, I guess it is 7 years or so, and it was a kit, and it was for about, I don't know, $40, $40, so you know, not really expensive. And today's you can get it for $20 from China, and you can buy it on the well-known Bay, and therefore no problem any longer. So that is what you basically need to determine a coax cable impedance. And I show you now how it works. And of course, for the wires, for the coax cables here are on my bench, I know of course the impedance, but as long we know the impedance, it is easy to prove that what we are doing is working just fine. I mean, this here is, you can't read it, so let me zoom it in. So this is a well-known cable. So this is a RG58, and of course you can read it already. It is 50 ohm, and therefore we know this is 50 ohm, so very good for us, because then we can prove that what we are doing will work. So I simply cut here a bit, so I do not measure the lengths. So you have seen I've simply cut it, and it is enough to have a piece like this. So it can be longer, it can be shorter, so no problem at all. So we need a little piece of the wire we want to test, and then let's see what we can do with it. Okay, and the only thing I've done so far is I've taken off the cable insulation from both ends, and that's it so far. And now our little meter here comes into game. And first of all, it is switched to capacitance, and we have to zero it out. So that is what it is by now. And now, very easy, we connect here our wire, our coax cable, to our meter. All right, so that is all we do. So this end is open, nothing happens to this end, and what we can read here on our meter is 37, and I write it down, 37.2 picofarad. So that is what the capacitance of the coax cable is here in this length. All right, so that is what we do. Second step, we flip it over to inductance test, and of course we have to zero it out once again, and we press our zero button, and now it is showing 0 microhenry. And now I just take one end and I twist it here simply together, right? So I twist it simply together. That is all I have done here, nothing special. And then again we connect our meter to the wire as we have done it before, and what we read so far is 0.10 microhenry, which is equal to 100 nanohenry. All right, so that's it. So we have now this both values, and now the magic starts. Alright, so that is what we have. So this here is our C, so the capacitance of exactly this length of our little RG58, and this is our L, alright, and 0.1 microhenry is equal to 100 nanohenry. So you can use it as it is more familiar to you. So both is definitely right. And what we are looking for is our cable impedance. And our cable impedance is that So that is known, and we expecting, of course, 50 ohm, as it is a normal RG58 coax cable, and we know, so this is a very well-known wire coax cable for our radio applications, and therefore we of course expect 50 ohm. And the nice thing we can use to determine our cable, our impedance of this cable, is a little formula we have. And the formula is that we have our square root out L over C. All right? So that is our formula. And if we put our measured figures here into this formula, then let's see if this works, what we have done here. So just measuring our C and measuring our L, and that we are able to determine with this both figures our Z. Is that really possible? Okay, let's try. So this is then equal to square root out of 100 nanofarad over 37.2 picofarad. And what now is the outcome? Let's see. Okay, and you already may see it. We need a calculator, but for all of you who have passed the ham radio examination, definitely have a little calculator. So let me bring this here into our game, and this is a calculator, maybe a little bit more modern one, so I really can type in the formula as it is, and therefore I have here our square root, and I can fill in now our 100 nanofarad minus 9, so that is 100 nanofarad, and divided by 37.2 picofarad, which is minus 12. I hope you all can agree on this. So you see now here in the calculator exactly what I have written down here. So maybe once again 100 nanofarad is equal 110 exponent minus 9 divided 33.10 minus 12. All right, so that is what it is written in a different manner, and that is what I can really type here into our calculator. And now when I press the equal button here on my calculator, let's see what the outcome is. Wow, and have a look. So that is really what we expected. So our calculator is telling us that it is 51.84 ohm. So that is the impedance we expected. And it is clear that we have some little variations because our little meter here does not work 100%. So our C or our L, what we measured, may be a little bit different to what our meter was reporting, and the wires here are not really good. So there are a lot of ways we can simply implement an error into our test setup. But after all, what we really can say that we are so close to 50 ohm that we can say, yes, this is a 50 ohm wire. And you know, that is all what we need. We need to be able to distinguish a 75 ohm cable from a 50 ohm, because this both coax cables are very often looks absolutely similar, because 75 ohm is used in this local network setup. So this LAN coax cable has 75 ohm, and as we already have heard, our coax cable for broadcast applications like your TV or your broadcast radio is using 75 ohm as well. So that is where you really need this most to distinguish a 75 ohm cable from a 50 ohm cable. And now let's prove that this really works. Because, all right, we have simply taken our RG58, but let me do exactly the same here with a 75 ohm wire. I mean, this is white, and simply from the color of the wire, you could assume that it is a 75 ohm wire, but we have 50 ohm wires in white as well. So it is sometimes really tricky, and therefore, once again, I do not measure the length. I just cut it here somewhere. All right, so that is what I have. Let me take off the insulation here, and then let's do exactly the same. Okay, so let's do exactly the same what we have done before. Okay, first let's test our C, and it is all right. Let's say C is equal to 10.98 whatever picofarad, so no problem. And now let's do the same for L. And of course I have twisted it together once again, just to have here a short, right? So as we have done it before. And our meter is 0 already. So let's connect it once again, and we read, let it write down, L is 0.06 microhenry, which is equal to 60 nanohenry. All right. All right, and I've already put the figures here into the calculator, and you see, of course, here are 60 nanohenry, and here are 10.9 picofarad, so that are the values we have tested. And let me now press here our equal button on the calculator, and let's see what the outcome is. Wow, and again, so we are very, very close. So 74.19. So it is clear that this wire here is for sure a 75 ohm broadband coax cable. And you see, it is really that easy to determine the impedance of an unknown coax wire. Okay, one more experiment. Will our little equation also work for this kind of wire? Alright, let's check it out. Okay, so again we connect our C meter to the wire, so exactly the same condition, and we read 9.8 picofarad. Okay, 9.8 picofarad, And now let's do exactly the same to get our L value. And when we do our L test, we read 1.56 microhenry. 1.56 microhenry. So that is what I have written down now, and now let's do our little mass. And here is our mass. I have already put all values in, and you see we are reading very close to 400, but it should be a 450 ohm wire, and the error is because I have done it like this, and you simply see that I really destroy here my values. So I shouldn't do it like this. I really need to put a little bridge over it, not to influence here our values, because now the distances are wrong, and yeah, so we have definitely a higher arrow doing it like this. Alright, so I have simply improved this short here a little bit to get it here better matched, if you like, and you already see that our value is improving already. So maybe our capacity is a little bit different to what we have measured, and you see this already is improving it a lot, so that it already gets closer. So you see, even with a wire like this, this little formula is working, and so you really can be sure that you are able to determine your wires. Whatever you need, you can do it like this. And you already may wonder why it doesn't matter what the length is of our piece where we tested our values. So it really doesn't matter. So you can take it longer or shorter. So maybe if it is a bit longer, you have a more accurate reading, but basically it really doesn't matter how long it is. It may be dependent on your tester. Because as you see, it really needs to go down into the nanohenry and down into the pico farad, and as longer the wire is, as bigger are these figures. So that might have an impact of what you are doing. But basically, if your tester is very accurate and is able to go down to the deepest values without a huge error, then it really doesn't matter. So the arrow we tested here on this wire is most likely due to the accuracy of our meter here, and therefore, if it would have been longer, maybe our accuracy would have been better. But anyways, basically, no matter how long it is, it always works. And the question is, why? And the answer is really as simple as it can be. So this here is the equivalent circuit diagram of a coax cable. All right. So what you see here is nothing else than that we have a lot of inductance here in line with the wire, and we have all these capacities. Okay. And now dependent where where you cut your cable, here or there or there or there, you see that the ratio of your inductance and your capacitance is always the same. So what we are looking here in our formula is really the ratio, and as the equivalent circuit diagram is like this, and even it is longer, the ratio of L and C is always the same, no matter how long your test piece is. So you know it is always the same ratio. So that is what you need to know. And as we already talked about coax cable, let me share some additional informations about coax cable. The graph we are looking at here is telling us the loss versus impedance, and research has found that with an impedance of 77 ohms we have really the lowest loss if we compare the different impedances. So we see, for instance, that here with a lower impedance, I mean, we could really do coax cable in any desired impedance value. But the questions always are, what is the best for our purposes? And we see with 77 ohm we have really the minimum ever possible loss compared with other impedances, and that is what this graph is showing us. So with a lower impedance we would have a higher loss, and with a higher impedance we have again the same. So for, yeah, let me say for receiving devices, 77 ohm would be the optimal impedance. And now you get maybe a first clue why we really use 75 ohm impedance coax cable for broadcast application, where we only have to manage receiving signals. And therefore, as this graph is telling us, 75 ohm is perfect. Well, alright, so if 75 ohm is so brilliant, so why don't we use it with our radios? And now our transmitter come into our consideration. And what you can see here is the maximum power handling of a coax cable. And what you simply see is that with a 30 ohm coax cable we would be able to handle the highest power until we have a voltage breakdown. So that means now we have not only receive, we have also transmit, and with transmit we have a completely different problem, because as you can see, if we go along here our maximum power, you see at let me say 75 ohm we are not really able to handle our high power. All right? So now we are a little bit in a problem. As for receiver, we know we should have 75 ohm, because then we have the lowest loss, and that is brilliant. But on the other hand, we can't use our 75 ohm broadcast coax cable, as 75 ohm is not really able to handle high power. And as we use a transmitter, so we want to transmit our signals, right? We need a coax cable which is able to handle high power. But on 30 ohm, where we have really the peak on maximum power handling, we would have really a bad receive performance. So what have we done? We put our impedance, our radio impedance, somewhere around 50 ohm. And with 50 ohm, so this is a kind of compromise. So we have still a high power handling, and on the other hand we have still an acceptable receive. So that means loss handling. So therefore that is the reason why our radio coax cables are 50 ohm and why our radios themselves are all matched to 50 ohm, because for a transmitter and receiver it is really the best impedance to handle our receive and our transmit. Alright, so that's it for today. I hope this information was of any value for you, and yeah, if you like this video, please give me a big thumb up, and catch you next time. Bye!